Ah, so my voice is audible, no, ma'am?
Yes, sir, it's clear.
Yes, it's clear, right? Okay.
Yeah.
So good evening, all participants who are attending this faculty development program. This is Naren presenting today from MS Ramaya University of Applied Sciences. So good evening to everybody present here. So I would like to welcome Dr. Sunil CK from Indian Institute of Information Technology, Dharwad campus. So last session we had a great talk on Gen AI models and trends. So today I take this privilege of welcoming Dr. Sunil CK. So Sunil sir has completed his PhD from NIT Surathkal. He has done a PhD in information technology, and he also finished his ME in software engineering from University College of Engineering affiliated to Bangalore University, and had completed his engineering BE from KVGCE College BTU, Belagavi. And his PhD thesis was on plant disease detection using deep learning based framework from NIT Surathkal. Sir has published a couple of papers, journal papers in Science Citation Index, and he has also a lot of conference papers to his merit. And Sir actually represented the All India Inter NIT Athletics, and he won 2 medals in the year 2022 held at NIT Jaipur. He won 6 medals in VTU athletics meet during 2007 and 2009. And he also Vishwesvaraya Technological University in inter-university athletes meet. And he also took part in various marathons, etc., and has won also in a few events. So, and he has also been, his hobbies include, he's interested in agriculture, he does yoga, he is also an athlete and also plays tennis. So currently, sir occupies the position, he's an assistant professor in the Department of Computer Science and Engineering at IIT, Indian Institute of Information Technology, Dharwad. Sir, on behalf of MS Ramaya University of Applied Sciences and its community, we, we welcome you for this particular FTP. And I welcome Sir to give a session on leveraging MLOps for HPC in data intensive applications. Over to you, sir. Thank you.
Yeah, thank you for the kind introduction.
Thank you, sir.
We'll start with the MLOps and HPC and distributed computing as a topic related to what the topic is mentioned there. So you all know that what is MLOps, say that it is called as machine learning operations, like as we have a DevOps. It has taken the principles from the DevOps to manage the machine learning life cycle. So usually, you all know that machine learning life cycle, whatever things are there in machine learning, what we use. So why we need MLOps usually? So in machine learning, we usually have many things like data preparations. In the first stage, usually we go, and once we start with the data preparation, we'll have to do some data aggregation, data labeling, then data wrangling, balancing the data. During the balancing the data, we will usually focus on how to clean it, how to normalize, and how to regularize the data. If the data is of, we have to make sure that the data is not biased one. Uh, and we will, if we find any biasness present in the data, then we will have to detect the where exactly the bias, and then have to mitigate such biases. And while once we collect the data, usually we do a data wrangling in such kind of thing. Then while collecting the data itself, we will be having the things such as data labeling or data annotation. That is a basic block of machine learning, right? Usually, machine learning or deep learning, whatever you used to do, basic work starts from like whatever the problem statement you are going to detect. So as soon as you detected a problem statement, you will be mainly focusing on the data. Without the data, we can't do anything related to machine learning or the deep learning. Say there, once you get the data labeling is one of the major concern will come in the picture, where whether it can be healthcare, data analytics, or it can be any other real-time applications. if you consider as a healthcare data analytics, we have to authenticate the data to some subject expert or what is the physician or the doctor has to verify and has to annotate the data for you. For example, we are coming from the technical background, we are not aware of what kind of data it is unless and until they labeling for us, right? That is what the thing we do. That we call once we labeling, we'll moving on to the feature engineering, such as feature importance, transformations, encoding, other things we do, and we are coming with some kind of data. So that will be helpful for our further process. Okay? That we call it as a pre-processing. So we call it as a pre-processing kind of thing. And once we do some pre-processing, then we will moving on to train and tune the model. So where we use usually different algorithms will come into the picture, right? We have to select some algorithms. Right? We have to select some algorithms which are capable to do some classifications or whatever the task we require to do, either it may be predictions or classifications. So we are going to that's what algorithm selections will come into the picture. There we do initially we may have seen, right? Usually, if you are involving in the research, usually we do some trial and error, or we'll be reading some literature. Several papers means we are doing some literature work, so that through the literature we'll come to know that what kind of algorithms can be fit for our data, right? Based on the data what we have identified. So what kind of algorithms is suited for us? We will be do some modifying, or we are going to develop our own algorithms also. So we call it as trial and error method. Right? We do some experiments with that, and we'll check with the results whether the results are appropriate or they are fruitful, right? Or we are going to develop a model, right? Once we identify the algorithm is finalized, then we'll move on to then we'll be moving on to developing the model, right? Model training. We are going to train the model. So as we are going to set some hyperparameters. The parameters usually it can be many hyperparameters you might have come across. So either it may be deep learning or machine learning. Usually machine learning will see the hyperparameters such as learning rate, or in the deep learning we say that optimizers or epochs. Epochs is also one of the regularizations. L1, L2 regularizations, whatever the thing we are going to use. And then once we finalize the model, then we are going to identify, while developing the model, we will be identifying what are the metrics can be used to validate the results, right? We have already annotated the data in the beginning, and once we come up with the model, then we will have to say that what are the metrics can be used to validate our result. Okay, there also we are going to use some of the hyperparameters to do that such a certain task. And once we develop the model is say that we are achieved some fruitful results, then we'll be moving on to deploy in the real-time environment. Right? We have developing the model, we may have to see to that like training and validations. Once we do that, when you go for the testing, once you complete the testing, we'll going for the deploy and monitor. There you are going to do actual real-time data will be come into the picture, right? There we can see that model deployment, and then if the things are working good, then it will be comes the pick where anybody can make use of those things. Whoever is the end user you have already targeted for. This is why how the machine learning life cycle used to come, right? So before that, we'll see that why the more what is that MLOps we need it, right? So there you can see what it does. MLOps is machine learning operations that refers to the practices and tools used to streamline and manage the life cycle of the machine learning models. What we have discussed so far now, as I said, what is the life cycle that they start from the data preparation to the deployment of a particular product or a particular model. So this is to be streamlined, and you have to manage the particular life cycle. Okay, from the development to the development and monitoring. Or we can, the other way we can define it as a set of practices to streamline the development, monitoring, and management of machine learning models in production. The main goal of the envelopes is to automate and standardize the machine learning workflows and improve the collaboration between the data scientists, engineers, and operations teams, whoever is involving in developing the model. It starts from the, as I told you, that data preparation itself, data collection itself, right? So, and ensure the reliability and scalability of machine learning models, and monitor the models after development for performance and any drift with that. So once we see you in day-to-day life, we are using so many ML algorithms are already been there in our mobile applications. If you take as mobile as one of the product, if you see, there are several applications that are running behind it. So there are several machine learning and deep learning algorithms are already being used in some of the applications. If you take it as a Gmail, okay, Gmail also does some of the jobs for you. Say that it will be segregate your email, whether it is social, whether it is spam, whether it is what is that, promotional, or it is like it is directly sent to you. These are all some of the things, right? These are all they are all the machine learning applications or the machine learning algorithms being used. This how we see the Gmail has been given you the product. They are continuously monitoring how the product can be make it better. Okay, based on the experience they see, right? So envelopes can be seen as a set of best practices for managing machine learning models in the production environments. This is what I have discussed so far. This is a picture where the life cycle of machine learning operations really relying on start with the data acquisitions, which are management. We have discussed that some of the concepts of data collection and ingestion, and data validation and annotation. As I said that in the beginning, so data validation is one of the important things, and we have to do some data explorations, data quality assessment. The quality of the data is more important. If we have the data having some noise, the data is not up to the mark, we may not expect what is fruitful results at the end. And data preparation and feature engineering can be done in the first one of the life cycle, you can say, and experiment and management and model development. What we have seen that model exploration, model training, model evaluation, and model selection, model fine tuning and validations. These are the things we are going to see. And then we will be go with the experimentation and development testing, production development. In that case, we are going to deploy the model monitoring, model management, and serving the predictions to the client, whoever may be the client. Okay, these are the things we usually generally see in the machine learning lifecycle. Right. Then this is how you can see the machine learning system look like. Where the MLOps comes, where the MLOps is going to machine learning operations you are going to keep, right? There you can see, say that whatever the things we have seen so far, the machine learning life cycles, data acquisition, whatever the development and production means deployment of the thing. So after that, we can see that what are the things are reliant for that, right? Once you come up with the particular model or development of the model, it has to run on some specified machine. Either it can be edge devices or it can be a server or somewhere. So usually, once the model is developed, it will be somewhere it has to run. Usually, for example, if you take it as a Google Gmail application or your WhatsApp application, or you are using some social media network, social media applications such as Instagram, Facebook, LinkedIn, whatever. Okay, they are all already running in some specified locations, right? They are already running in backend, but those applications has to run once they're what is that? You are installed in your mobile, so it needs some memory to run on your machine, right? So how does that model run? Like there are kind of some applications, right? So they are having some machine learning models being running behind it. So for that, you can see some, you need to have some right architecture for the product has to be run. So there you can see that some of the considerations you have to use, say that what are the common architecture or common patterns for ML or some of the, see that the application to run on something, it should have some compatible devices, right? Various you can see the various development and deployment patterns that depend on the problem and with the data you use. So this is how you can see that where the applications interfaces happens once you see develop the model and deploy the model, where the product users or other consumers. Okay, you can see that downstream systems, etc. Then overall business runs upon that. This is how the actual machine learning MLOps runs, right? So we'll see some of the common architectures that can be used in case of development to run the some of the MLOps. So some of the things we can say that dynamic training architecture, where we can see that event-based training architecture, which is also called push-based. There, the training architecture for the event-based scenario here, whatever the scenarios you are going to say, such as if you want to stream the data into different warehouses, okay, that causes some trigger, okay, depending on the concept, where you can see the workflow orchestration tool that helps to the workflow and interaction between the different warehouses, data warehouses, where the data, what is the data pipeline, what are the features are involving there, okay, and the processing thing. Or if you are using some brokers such as servers has the works as a middleman to help to coordinate the process between the data job and the training job. We can see the data warehouse is there, the trigger component is there. So where it is it has some coordination between all these things, right? When the data is coming from the different sources, either it can be mobile, or it can be computer, or it can be from the server, whatever the data storage system, and it is taking the data from the different sources, and you are going to make some data pipeline, and training pipeline will keep on communicating with the uh, data pipeline and the thing. Okay. So, or you may have the message broker will be there to serve as a middleman to help the coordinate process between the data job and the training job. Okay, so in on orchestrated pool-based training architecture is another one dynamic architecture can be used. For example, the data ingestion from and different IoT devices or stream analytics or online serving, right? So in such scenarios where you have to retain your model at scheduled interval, okay, and your model is waiting in the data warehouse, and workflow orchestration tool is used to schedule the extraction and processing, uh, and also it does some returning of the model on fresh data, right? Whatever the data is going, it is like the data is like which it has to run on the fresh data. So this is particularly useful for problems where users don't need real-time scoring, like content, for example, recommendations, such as you are using some mobile applications for you say Ticana, or you are using some Geo Savan or Spotify, some kind of things. Okay, they serve pre-computed model and recommendations when users log into there whenever you are logging to there. Right? You are going to get based on your mood. For example, Geo7 used to give an advertisement say that based on the user mood, it is going to stream some of the music. Such kind of advertisements you might have seen, right? So next is of message-based training architecture. This architecture is useful when you need continuous model training. So the model has to train continuously where new data arrives from different sources. As we say that mobile applications like web interactions, it can be any other data source, right? So data is coming from continuously data is usually feed into your thing. You need to train for a newer data. Then the new data arrives, then you have to update that. Okay. So the data service that can subscribe to the message broker there, okay, whatever the data is coming from the data source. Then when data comes into the data warehouses, it pushes the message to the message broker here, okay, data warehouse to the data message broker. Then it will send the data to a message to the data pipeline, okay, where the pipeline is to extract data from the different warehouses. So once the data is there in the pipeline, it's streamed to the data storage. The data in the data transformer data storage or feature store will come into the picture where that may data will be message pushed to the broker and again send message to the training pipeline to load data from the storage and pick up for a training job. It will be doing continuously. The process is like a cycle. The thing will come from the data storage and it will be training. Means the data pipeline will take it and transform the thing. Okay, it will keep on going. So if user triggered for training architecture, where a user sends a request to the training pipeline service to begin for training based on the availability of the data. Okay, that how does it work? So some of the things are for the static training architecture, where if you see the dynamic training means where the data is real, right? For example, if you are using IoT devices will send the data continuously, right? Once in often, like for example, if you set based on your threshold or based on your timestamp, it keep on sending the data. So as I given some mobile applications, such as the more music application, so that is taking the input, right? As soon as you change some application, means change your listening pattern, it is automatically it has to change its pattern to feed the music. And most of the cases, if you're using the applications such as Netflix, Amazon Prime, Hotstar, so there also it is based on your feed, okay, based on you changing the pattern. For example, you are changing some of the videos you're watching in your Instagram, okay, it will feed based on your like, based on your comment, or based on your search history, right? Based on search history, you are going to get some feeds in Instagram or YouTube, usually in the shorts, YouTube shorts or Instagram shorts there. And same thing will happen with the other applications such as Netflix and Geo Hotstar if you're using them more TV applications. So where the static training architecture like comes. So your data distribution does not change much, right? In the previous applications, what we have seen, the data is continuously changing. So here we are going to see to that the data doesn't change much from what you are trained for the offline mode. And for example, if we take somebody is taking the loan, okay, you need to approval for the loan approval, where the attributes need to decide whether to approve the loan or deny. So there it is based on certain conditions is already being set. Okay, so you are already known that what criteria you want to see. For example, CIBIL score, credit score, or CIBIL score being used in most of the banking sectors. They are aware of the person's things. Okay, it will be looking for that, and it is already been said that, okay, so and so things can be done. For example, it is above 700 CIBIL score or above 600 CIBIL score. Okay, if it is below 300, what to be done? These are already fixed in that particular thing. So we call the things as somewhat it is static one. There you don't need to change much. Okay, that already been trained. Okay, it will done as per that. Okay, there you can see that. The data storage and model code will be there, and you have already trained the model. Your model is already deployed, and it's going to do some predictions, okay, based on the data it is going to take. Means the much changes may not be there, right? So some of the serving architectures, you can see that batch architectural patterns. So in case of batch architectural patterns, you can say that it is doing as like a batch, so that it takes the your model usually makes predictions offline and puts the things data into the storage that can be served on demand. Okay, based on user demand, it's going to do some of the tasks. You can see here. It is based on the serving pattern. If there is whatever the things you are going to use, like your server and client thing. Client requested something. Okay, send scores. Okay, as I given as example, like so some banks wanted to know the content of some particular customers. Okay, so that you're going to send something, you're going to request something to certain user ID, and you're going to get some results from the other end. So there it is like kind of client server architecture. And next one is in serving architecture, again online or real-time architectural patterns. It is similar to the dynamic one again here. You are going to serve in real time. So as I give an example, one of the mobile applications we have seen, and here also you are going to say that it is served model. It's going to serve for the certain task. Say the client is requesting for something, and through the API communication gateway, it reads some client request from the other server model. For example, you are going to ask ChatGPT, DeepSeek, or what is the Perplexity. Some of the applications are evolved. Many other applications where what you are going to do, you are going to ask, so that it will that you are going to make use of the API calls, right? So that you can make use of the API calls to the ChatGPT as well as other applications. If the ChatGPT does the same thing, it will be it does some request from other, right? And it gets the scores or it gets the content and it is sending back to the client. This is how the things works with that in case of real-time architectural patterns, or you can say that online, we call something like that. So how we are going to select some of the architecture for your project? So you need to know that what project is best suited for you. So if you say you have come across some of the problem, so you wanted to select that this architecture will work for me. That you should say that we have seen some of the architectures. It can be dynamic or it can be static, whatever the served architectural pattern. So you need to figure it out which architectural pattern for suits for your applications, whatever the applications you are going to develop. So it will design. It will be depending on what operational excellences you are looking for, what security you are interested in. For example, whether the data is protected, whether the data privacy challenges will be there, and and reliability of your product. You need to focusing on how reliable, right, your product is, like ability of the system to recover from infrastructure, or is there any disruptions with respect to the services, and you are encounter some computational crunch, like the downtime in the server or downtime in the your possible computational infrastructure, and performance efficiency, like as I told, that computing resources, okay, and maintaining the efficiency as the demand changes. Say that if your If, for example, if you go to the ChatGPT earlier days, okay, everybody is making use of the ChatGPT. It is difficult to answer at that particular time. The capacity was less. For example, if you do go with the DeepSeek, as soon as it got popularity, so most of the people are using at a time, then the efficiency will be less, right? So as if you see to the real time in government government services, for example, if they ask for some applications, so usually the last day rush should be there and the server will be down. Right? There are performance efficiencies there you have to check for. So you have to maintain the efficiency as the demand changes, and if the technologies are evolved with the new thing, you will have to update. And how you are going to do with the cost optimizations. So you are going to operate like cost-aware machine learning systems that achieve business outcomes, and it has to minimize the cost for you based on whatever the computational resources you are going to use or manpower you are going to use. So it has to minimize the investment, and it has to maximize the your revenue or your return, whatever that you made the investment. So there you are going to look for many things, like as I said, that operational excellence, where you are going to deal with, you have to say that continuously monitor and measure the ML workloads, whatever the machine learning algorithms you are using, that you have to see to that whether they're up to date or whether you need to update with the new model or what, and have to establish the model returning strategies as you wanted to go for the automations, you have to replace some of the things. You have to minimize the human intervention. There, nowadays it is happening, right? You can see to that where most of the things are agentic, like the things are done by the agents, like some of the customer care services are done by the agents. Like earlier, it was started with the chatbots, so the chatbots used to answer. Now the agents are going to do some of the tasks for you, right? So automate machine learning and deployment pipeline. So where you will look for the security, as I told you, that restrict some of the systems, ensure the data governance and data privacy, data lineage, right, and regularity compliances with the government, and you will have to see to that train a model once and deploy across different environments, and you have to look for the performance. As I told you, you have to optimize the computational resources for the whatever the ML operations, ML algorithms you are using, and you will have to continuously monitor and measure the system performance to give the better uh, performance, right? And you will have to look for the some cost associated with the your machine model. So if you take this example here, what is displaying? So this is if you take this is an example for some if you take a scenario says that some recommendations have to be given based on the news article. Okay. So how you are going to give some recommendations? So whether they has to go with the subscribe, or see if you are using, for example, if you take it as a your Netflix, what is that? Yeah, some of the applications you are using in day-to-day life, such as Netflix, JioStar, JioTV, something. There you can see that how you can give some recommendations. Okay, in that view, this example you can able to see. Uh, so first you will have to understand what's your business. Okay, in such cases. Okay, so assume that your business is like in several places, and you have to see to that many people are using your many are there as a subscribers. For example, if you take it as a Netflix and Airtel, what is it, Amazon Prime. There are many users are there for Amazon Prime as well as the Netflix nowadays. So if you go back to some years, okay, where before the Netflix has come into the picture, Amazon Prime or OTTs, okay, where there was a industry in America where they were the most popular one, where they were giving the they were selling the what is that movies, okay, after the release. So they have the stations, they have the stores to sell those things. People used to buy and people used to watch, as like what we do VCD, something we used to say uh, earlier days before we used to keep it in our devices and we used to watch and we used to return that particular uh, cassettes or something. Okay, that was the business was running. They were not aware of that OTT used to come and take their demand. So that's what they were relying on the users. Okay, now the most of the things are relying on the subscribers, right? What are the different subscribers you have? So based on the subscribers, you will have to give like so based on subscribers as well as the user experiences, you will have to give some informations, or you will have to serve the user, right? So that's how you will look for your business goal, how you are going to manage with the businesses, and you will have to find some of the business metrics for you, and you'll have to see to that how you are going to serve as the more number of subscribers are coming to your this one. Okay, so assume that you have some certain subscribers, like some thousand or something, then keep suddenly the subscribers are increasing. So how you are going to handle the thing? Okay. So you can see the infrastructure in this diagram, like you're going to see that web client will be there, mobile client will be there, their unique ID for user when they log into that, and article recommendations for the user. So it's like work as a backend. Okay, so as soon as here, if you see this new article has come, the data transformations, the pipeline will be there, and performance monitoring services. You can see ground truth table, prediction details, monitoring data pipeline. Okay, that generates some report, and that is an input to the recommendation system where there are certain APIs. They look for the recommendations already stored for such user, making use of those things and read the user ID model registry. Okay, it does something, and here you have already trained the model with respect to the feature store, how developed for as per your collection, and it runs in that, and you're going to recommend to the user, right? You in that case you have to understand what data you are collecting, what are the requirements, you will have to see to that, and so based on right, certain other things you are going to see to delivering some content to that. So what is like how you are going to connect your thing MLOps with HPC? So what do you mean by HPC? I hope you've already got that some idea that you are using the applications such as Geo Hotstar, or Amazon Prime, or Netflix. There, the things have to run in a certain device, right? For example, if you go with the ChatGPT, uh, some certain applications where the users are more. For example, if you take it as a Google as one of the things there, the users are more. They need certain computers, right? So what high performance computers means? It involves using powerful computation systems like supercomputers or clusters of high performance processors usually be there to solve complex problems that require a lot of computational power, such as simulations, large-scale data processing, and scientific calculation. If you see a basic example as the Google and ChatGPT, where several people are asked questions, but some are bad questions, some are nonsense questions, some are relevant questions. Okay, for simple things also people used to ask. Okay, it has to handle such things, right? It has to that need a lot of computational power, right? If you go with the systems, like if you take it as an what is that? If you consider our what is that? A defense system or weather forecasting systems, okay, they're all running on some certain supercomputers to get and analyze the things and get you some the details for the public use, right? So the high performance computing systems that provide massive computational resources to clusters such as GPUs, accelerators, and specialized uh, interconnects. Okay. So there, most of the things you can see there, the training used to happen in the offline, and are they are looking for the data in real time and continuously training, as you say that ChatGPT is one of the examples, continuously training, right? As soon as the person is asking some data, it is taking as an input and it keep on training with with whatever the things is being asked. For example, now if you see that Perplexity is given, and Google also has given some offer to the certain users. They wanted to know, they wanted to collect some of the data, right? So the Perplexity is learning. They are all training such models in some supercomputers using several GPUs being used. They have given free for most of the Airtel users, right? That was the advertisement they have given now. So all Airtel users are using the Perplexity. So everybody is keep on asking some questions, keep on searching or looking into some information. So they are training the model based on the user things, right? So there they need certain computational resources, right? They run things in several GPUs. Uh, Okay, and while HPCs is often used to traditional scientific computing, it's also becoming relevant for machine learning and AI tasks due to their high computational demand. If you see whatever the applications you are going to use, say for example, if it's say Facebook or Instagram, they are daily basis they are receiving a lot of show that what is that what do you say the some feeding from the user. Either it can be watching history, or it can be like, or it can be comment, or it can be the content from the what is the influencers or whoever you are going to post, whatever may be the user. So such things are to be, they are considered as the data. The data is very huge. Such data has to be run on such high computational models or high computational devices. Right? So the demand is more for certain things. So usually differentiated from ML workloads due to high precision floating point requirements is required to handle such things, and more CPU than GPU uses. Also, lots of proprietary specialized softwares are required. Okay, large high performance computing clusters are very hard to build and many in-house. So this is how we can see to the HPC, high performance computing. And then we can see that MLOps can reach scalability ceiling for how we are going to connect usually. Computing resources due to amount of data and training. So most of the things have to be trained, right, in such a devices. So we generally what we do is like we do some of the small applications we are going to develop so that we feel that our computer is enough. Sometimes we may see that like our computer may not be sufficient for us, right? We will be relying on some. We will be looking for some better computing devices. We will be most of the places, most of the times we'll be looking for some GPUs are available for us to develop. What is that? Design or sorry, train the model. Right? We'll be focusing on that. And that's what we are going to say, that MLOps can reach scalability ceiling for computational resources due to the amount of data and training. Our solution is utilizing high performance computing environment. Many scientists utilize HPC for machine learning, but not to have a proper MLOps workflow in place. Right? So you see that MLOps, how for HPC there. So bringing DevOps or MLOps principles such as automation, CI/CD, producibility, monitoring things into the high-performance computing ecosystem, which traditionally was not designed for agile machine learning workflows. Okay. So how we are going to do the link between MLOps and HPC, where infrastructure management, HPC, data handling, and integrating MLOps with the HPC infrastructure, improving model management, and okay. So infrastructure management in both fields, you need sophisticated infrastructure to manage the workloads. As we have seen so far with MLOps, this includes the deployment pipeline, model monitoring, and scaling of ML workflows, all which require an understanding of the systems level optimization, something that HPC also emphasizes. So it means as you see, so that ML, machine learning life cycle, this involving many things. Okay, all such things has to happen as if you go with the operations. Okay, that done with that. So you are going to make it as an automations. There, it has to run in certain computation, certain computing resources. So you have to handle the data where the data is huge, assuming that. So HPC systems are optimized for handling and processing massive amounts of data, similar to how MLOps handles large data sets for training the ML model. Right, ML are deep learning models. We usually see to that they has to run. They need a computational device. So integrating MLOps with HPC infrastructure, where organizations currently using traditional HPC systems can benefit from adopting MLOps frameworks to modernize their ML workflow and make them more efficient, automated, and scalable. And improving the model management, like by using certain tools and practices from both the machine learning operations and high performance computing, and organizations can better handle the complexities of managing the models and monitoring them in productions and ensuring the scale effectively. Challenges of high performance computing like as large scale distributed systems, right? So high networking bandwidth are requirements. The most of the systems are distributed across different locations or different geographical areas. So the systems are distributed in many things. So you need to have a high networking and high bandwidth requirements are essential to handle something. And workloads will be there, tight integrations of software, hardware or software, or large scale cluster management, uh, right? And high precision floating point operations, as we have seen, we discussed earlier, that requires specialized hardware or specialized combinations of hardware or software required. These are some of the challenges associated with the high performance computing devices. So you will have to handle such things to derive giving some solution, uh, making use of MLOps and high performance computing. So machine learning works in part because of the massive data sets and billions of parameters. In these cases, running experiments on a single machine is not just is just slow. Right? You'll have to give the service in real time. So as we have seen that you're going to see the things in uh, the information comes from the in real time, right? For example, training a model with the say that 175 billion parameters, it would take around 288 years on single NVIDIA V100 GPU. If you say that GPU, for example, if you are doing some experiment, we will be relying on one GPU. Usually, we expect at least one GPU supposed to be there to do some of the tasks. Right? So you see that these are the number of billion parameters are there. Then it requires, if you are going to run on one device, it will take around 288 years to do that. So it is often impossible due to hardware limits. Either the training data is too large or the model scale exceeds what a single card can handle. In this case, you will go with an MLOps platform with the right working plane configuration and implementation. So where you can use of the distributed computing, uh, you can make use of that. So that that says you can unlock scale not enabled for single machines. That says that significantly reduce training time, so that enable the faster iterations to achieve the model goals and optimize the utilization of available devices. So what about the devices that are available? Uh, Okay, if you take some typical scenario where the data involves a data scientist developing experiment code locally and needing to scale it to handle much larger data set and or to distribute the layers of larger model across multiple devices. Okay, this often needs to be achieved within a concise time frame. So if you assume the model fits on a single device for certain examples, but the data set is large, okay, in that case, you will have, consequently you will have to employ the popular distributed or parallel strategy, or distributed computing or parallel computing. You will need to employ. If you explore the options of achieving a certain such goals, you will have to examine the required code adjustments and deployment processes for different environment organizations. So, so in such cases, the distributed processing strategies usually come into the picture. So, where you are going to train the model, train machine learning models on such massive data sets using traditional search sequential methods. So that often leads to long training times, as we have seen that low efficiency. So if you're training the model, and you see, as we give an example, such as day-to-day life, what we use nowadays, that GPTs we use. So they has to train, okay, and they has to train in real time, and they has to give the results on time. Otherwise, who will go and use such models, right? For example, you are asking something, and it is not able to give you certain results on certain time. Right? Nobody will be interested in that. For example, you might have seen you might have experienced, right? You were using the such GPTs or DeepSeek. Sometimes it used to take some time. It may say that many people are using hold on or something, right? You will have to such efficiency, you will have to improvise through the model. Okay, where while optimizations methods like you can sequential training, adjusting numerical precision, or upgrading to bigger GPUs can help. Okay, the height limit as model size or data volume grows. Right, you need to give some result in on time. For example, you are surfing, you are using the Instagram, you are looking for the reel, so that the reel has to flow as per your mood, right? For example, we have seen that you're listening to some certain music. The music has to come the next. Usually, you don't want to skip the music. You don't want to go for the next song or something. That you're expecting the thing. Application has to give you as per your requirement. That's what most of the user look for, right? So whoever it may be. So, for example, you are searching in a Google. You are expecting most relevant informations. It has to listed on the top. Okay. Otherwise, you'll feel like bad. Right? That's what customer satisfaction. So how we are going to do such things, right? For models that can't be trained or served without distributed methods, consider large models. In such case, you can go with LLMs like GPT, Llama model, which contain trillions of parameters. These models can't be trained on a single GPU. As a given, they simply do not fit into the device's memory limit. Even smaller models trained on petabyte scale data sets. Okay. As give an example, as recommendation system sets and Netflix or Amazon, there you can see that recommendations will come as per your requirement, right? That has to happen. Thing. For example, you are using some mobile applications developed, and you are using the mobile application, right? That has to run on your device. Okay? But in the back, whatever the services are come from the different locations, right? As you see, the ChatGPT is an application you are using, but things are happening in a different server, different devices. So where you face a distributed or nothing, okay, lemma, as strong and processing such data on a single machine is impractical. So you need multiple devices and multiple there when you're looking for the certain computing device. So distributed strategies balance the computational load and memory footprint by partitioning the model and data sets across across multiple nodes. So this improves the scalability and efficiency, unlocking training capabilities that single device techniques can't achieve. So initially, you can see that the distributing processing systems in the machine learning, the focus is mainly on the two things. One is like parameter servers and collective collective peer-to-peer communication primitives like the ring-based. You can see that the first one, parameter server, where you can see it like you might have seen that big data analytics, where you can see that the client and server, something like that. Here also you can see that the parameter server, there the things work with the different workers like work A and work B, or whatever the number of workers are there for that. Okay, the gradients and parameters are interchanging with that. So let's say that parameter server architecture may use more bandwidth and resources, but can be fault tolerant and support asynchronous updates. It is fault tolerant. In one of the worker is being failed, the other worker is there to respond and is there to take care of the thing. Right? And while coming to the other side, if you see that the P2P communication primitives, it uses less bandwidth, but are mostly synchronous, potentially limiting fault tolerance and performance in high latency networks. Say you can see that if you are using ML-based solutions, okay, if you see that advancements in the hardware and stable implementations, you see to that you can see the parameter server paradigm is useful for federated learning, where with varying device access, like your data is come from the different devices. The data usually the federated learning is the given feature as data privacy. Netflix, your feeds are an input for that, but they maintain some privacy for that, right? You are getting for certain users, certain workers kind of thing, right? It involves two entities. There, the parameter server, which manages the model parameters, and workers, which compute on data subsets and synchronize independently with the server for updates. This approach usually handles work failures well, but adds complexity and requires careful balancing of the worker to server issue. So you see that it requires more computational power to handle the thing, right? Two pure parameter servers can cause network communications bottleneck. So you need to have such bandwidth to handle the large pool of users. As an example given as GPT, Google, Amazon. See, you say you take an example as what is it? The day used to come, big billion day, something, okay, something like that. So they used to handle as many people in certain days. Most of the people, okay, especially in India, if something, if you say that something free is available, everybody will go and take it. So most of the people will log into such things, right? So there you need to handle the certain devices supposed to be there to handle such things, to give certain results for the people, right? So most of the, you can see that the ChatGPT again, so it has to give the thing personalized one. If you go with the Netflix, again it is giving you the service in personalized services you are going to get. Several other applications you can observe, right? So where the data parallelism we used to come, where the model has to run in the parallel to get you some results, right? So for models that fit on a single device but require larger batch sizes or faster experimentation. So here the model usually is copied across multiple processes or machines, where each process a subset of data in parallel. See in the example, you have a device, you are going to give data is distributed among the different device 0, device 1, and device 3 to handle certain things. Okay. So for example, you want to train certain models. We have independency is there. Your model can run independency is there with respect to the data. That thing can run on different devices, right? So as like federated learning, right? Something like that. And next one, like you have to go for the tensor parallelism as like a data parallelism. You have done the data is parallelized so that it will be running on different devices, right? Some data is running on device 0, some is on data or device 1, some devices, some are on device 3. Right? You will be running on different devices. So where you will have to see to that dependencies that in such cases it is running on the thing in different devices. And it is come with the final results. It is not completely independent with one another, but the data dependencies is minimal, okay, in such case. So the tensor parallelism usually comes where the models with tensor so big that the data don't fit on a single device. If you take it, okay, here the model is split horizontally. Okay, each device think of the tensor and in parallel, and the results are synchronized at the end. Okay, finally the results will be synchronized once the things are run in the different devices. As it means you are going to distribute the tensor to the different devices. In the previous case, we have seen that data has been distributed among the different devices. Here you are going to distribute the tensor. If the tensor is too big, that's what model you're going to run on the different model. So, okay. In the previous case, you can see the model is same, but devices are different. The same model, but you are running the things on different devices. Right. But in this case, you can see that data is means you are running the things on different models. The model 0, model 1, and model 3. So data is not what do you say? Model is not same. The model is different from one another. And this is what you can see the distributing the tensor. Okay. So each device processes a sync of the tensor in the parallel. The results are synchronized at the end. Depending on the model, tensor parallelism may require greater network bandwidth and a single node with multiple devices to address the required throughput. And you can do the pipeline parallelism as like tensor and data parallelism. So you can where the data parallelism comes for sequential models with many layers, such as neural networks are transformers that exceed the memory capacity of a single machine, such as we can go with the pipeline parallelism is suggested in such cases. Here, the model is split into two stages, each assigned to a separate device or a node, allowing for overlapping computation and communication. See how the pipeline is parallelism. See that stage 1, stage 2, stage 3, stage 4. So data also can be parallelized in certain stages. So the next is the combinations of different parallelisms. We are going to make use of the things here, like whatever the different parallelisms we have seen so far, data parallelism, pipeline parallelism, and what is more like tensor parallelism. Okay, how we are going to combine of different such parallelism strategies is used for large models with billions of parameters. So where you can use approaches like zero redundancy optimizers or fully shared data parallel. You can choose optimal performance for certain tasks, and additionally, multi-dimensional hybrid strategies can be applied to break down more significant problems into smaller and manageable problems. You can make use of certain parallelisms, what we have seen so far, can handle such things. Okay. Here the data is there, data can be, you can feed to the different places. Okay. So certain things what we have seen so far can be handled. Okay, so distributed processing strategies are crucial for modern machine learning things. As we see that data come from the different sources, it has to run in different locations, right? So from parameter servers and peer-to-peer collectives to hybrid techniques such as what we are seeing in the Zero and FSDP. Each strategy addresses some specific challenges such as scalability, efficiency, and resource constraints. Right? The resource constraint is the major one, and you have to use the data, whatever the model is supposed to be efficient, and they need to handle the scalability. Like, okay. So whether splitting the data across devices, such as data parallelism, or you're going to slicing the tensors, called as tensor parallelism, or chaining the layers across the nodes using the pipeline parallelism. That's such choices depending on the model, whatever the model you wanted to use. Okay, the size of the model, whatever data involving in such machine learning are different things, and the infrastructure you are using. Okay, so depending on all such things to whether to choose what kind of things you want to rely on. So distributing the experimental code as training machine learning models, that the scale often hits a wall when fine-tuning the larger architectures are expanded, where single device setups get overhead, pushing teams to adopt distributed solutions. And however, you are to migrating from local experiments to distributed environments introduces some hurdles. Say that you wanted to run. Okay, you say that the model is same, but you are running on different devices. Okay, different distributed environments you wanted to run. Fine. How about if the data is somewhat it is independent? Okay, such hurdles will come. Right, the data is depending. Okay, some of the data is depending, so your recommendations may not be accurate. It may not be more than 90%. It may be around 70%. So this may occur. Teams must rework code for multi-device communications, manage fragmented data, and adopt workflows designed for small-scale prototyping. And data science space with unfamiliar tools. Sometimes it's day-to-day life. You may see that things are evolving, and you may see that different tools used to arrive. Okay, so whoever is working on it, they face that unfamiliar tools are being evolved. We have also experienced, right, in day-to-day life, the thing comes, we'll have to adapt to this. Okay, debug across the different nodes and balancing efficiency with the added complexity in their daily tasks. These are all the things are usually faced by the data scientists, right? Whoever is worked with that. So modern machine learning libraries, frameworks such as PyTorch, TensorFlow, Paddle for model training. So usually in day-to-day life we are using these are the frameworks for to train to develop the machine learning model. And they serve Tritron inference server or VLLM. They are serving as they are providing the distributed strategies through user-friendly APIs and models. So despite these, ASOP use these implementations offer enabling locally developed experiment to run in distributed environments typically requires some of the modifications. Say that distributing the model, the device must communicate after.
Sunil sir?
Yes, ma'am.
Actually, there is some disturbance with your voice, sir. Audio.
It's from beginning?
Yeah, actually, it is not clear.
Is it okay?
Maybe if there is a pass, it is okay. Yes, sir.
Okay.
Ah.
Some sound is coming.
Sorry, sir.
Is there some background noise is coming?
No, not background noise, but audio is not clear, is what audience are telling.
Okay, I'm not sure about it. Shall I speak a bit louder? Is that fine?
Yes, sir. Maybe. Yeah, maybe.
I'll see to that I can. Because I'm not here. I'll just check. I'll just check 1 minute.
Yes, sir. You please proceed, sir, but you just increase the voice. That will be enough, I think.
Okay, ma'am. Okay.
Yes, sir.
We were there here. Distributing the model, devices must communicate after such each epoch to share variant calculations or managing model layers across the devices. This can be implemented manually using available collective operations or handled by wrapping the model in distributed wrappers provided by certain frameworks, so that you can make use. You say that PyTorch been used where you can make use of the parallel things, as the parallel or distributed data parallel can be used in case of the PyTorch, and you can TensorFlow, you can make use of the distribute dot strategy to distribute the model, right? And parallel you can use the distributed dot data parallel. These are some of the uh, available frameworks and data wrappers you can make use. And distributing the data set, how you are going to distribute the data set among the different distributed systems. Here, similar to the data model distribution challenge, the data set must be split between the different devices, as we have seen in that picture. Say that the model is same, but the data set is of different. Means you're going to run this on the same model with a different devices with the same crunch of the data, right? And again, this can be done manually or using modules provided by the framework, such as in PyTorch is provided the modules such as distributed sampler. In TensorFlow, you can see that the distributed dataset with the strategies, say that strategy.experimental distributed dataset, and Paddle is providing this distributed batch sampler. And you can see that how to load the data, and you can do sample machine learning code here. And process the group management, where to manage the number of training entities, communications, and resource allocations for each worker, and effectively integrate with the distributed model and data set implementations. You are going to do the making the process group management here. For that, you can say that all the three different frameworks, you can see that they're distributed with the initiating process group and multi-worker mirrored strategy and in parallel underscore environment. These are the some of the things you can see. And defining the communication strategies depending on the chosen the distribution strategy. The following you need to consider, say that implement the parameter server or configure the P2P connective strategy. Okay, whatever you want to relying on, select and configure the appropriate communications backend, such as RPCs, Glue, MPI, UCC, NCCL. Okay, so things can be used by the process group, whatever the process thing. And training loop modifications, you're going to say that when managing the custom training loop, it might be required to update it to handle the distributed model and dataset. Okay, for example, you are doing some training loop modifications, you will have to take care of whether the data is distributed or the model is distributed. Like, so you are training on the different models or different machines or the different data sets. Okay, so things you might have to take care of. It's a training loop is been happening. So migrating from local experiments to distributed environments may seem daunting at first, require code modifications for model and data set partitioning, communication setup, and process group management. These are the main primary tasks you will have to look for. Say that you will have to see to that whatever the code is supposed to be modified as per the model and data, you will have to partition, and the whatever the communication setups that's the things I will have to take care. So the benefits far outweigh for these challenges. The modern frameworks have simplified much of the complexities, that allowing data scientists to harness distributed the processing with the minimal friction. There you can see by distributing models and data across multiple devices, teams can overcome memory constraints, accelerate training times, and scale their experiments to new level. Say, for example, you are saying that the data is being distributed among model is also distributed and data is also distributed among multiple devices. Okay, so teams has to overcome such memory constraints. So, for example, say that will have to accelerate the training time and you'll have to scale with the experiments. Okay, so this transition enhances the efficiency and also unlocks the potential for with a larger data set and more sophisticated architectures. So, and paving the way for robust production and ready machine learning systems. Okay, from prototype to production scaling with purpose, you'll have to see to that distributed training that addresses some of the critical barriers in the modern machine learning thing. So there you can see that models too large for single devices. Say that some of the models has been developed, they has to run on, say, they should run in edge devices. Say that mobile is considered as one of the edge devices. Nowadays, the traffic signal cameras are considered as edge devices. Whatever. So whatever the model you develop, that may be too large to run on such devices, single devices. Data sets too vast for sequential processing and timelines too tight for insufficient workflows. Where you say that if you take it as a traffic signal, where we consider as a what is that edge devices, your model, whatever the model you train, it should run on that particular device, right? It should take this action right away. Say that some like traffic violations or many things. You can see that in traffic scenarios, that camera has to whatever the model is being deployed in the camera, they has to work on time, right? So the data is huge for such devices. Whatever the inflow data it has to take in real time and it has to process it and it has to come up with the things. Okay, so that is one of the example I have given. Like that, it may be difficult to run. The model is too heavy. It is difficult to run on such devices. Your model has to come up with the lightweight model. Distributing workloads across devices unlocks scalability, accelerating training, overcome memory limits, and enabling architects once deemed impractical. Okay? If you see that it's impractical, you have to see to that. Okay, distributing the workloads across the devices. Okay, so to say that different devices are available and accelerate the training of your model, and you have to overcome such memory, whatever the memory limits you have come across. So the actual value of these strategies emerges only when models transition from experimentations to deployment, right? Once you've done the experiment and you will have to go for deployed such model. So that's what where it comes into the picture, right? Well, the example I have given is the traffic camera. Okay, you have already developed your model on your own, some other device. Okay, the device may be sophisticated for you. Once you come to the real-time testing, it may not be you are not able to do that. Okay, so you have to take care of other things. So deploying to distributed environment bridges the gaps between the theoretical gains and real-time impact, where depending on the team and organization size, configurations can range from local setups with the multiple GPUs. Okay, say that you are going to make use of the different GPUs are kept in a different locations. Okay, say that developer workstations are to small scale clusters of connected machines. Cloud-based instances you may use, such as Amazon Workspaces, EC2 or enterprise levels in data centers. So each tier introduces unique challenges like balancing the cost, network latencies. These are some of the challenges you may see. So you'll have to balance the cost associated with that. You will have to look into the latency, the network latencies, okay, the bandwidth of the network, hardware compatibility. Okay, these are all some of the challenges. Okay, but shares a common goal, that is maximizing the resources efficiency while minimizing the complexity. This was the primary goal of it. While implementations of the frameworks like PyTorch, TensorFlow, Paddle follows similar principles. So by training a simple linear layer model in a distributed setup, what we have seen in the example, so where we have to highlight universal workflows, okay, such as process group initializations, gradient synchronizations, dataset partitioning that apply broadly across frameworks and infrastructures. So what are the practical deployment strategies you may see? So adopt workflows to infrastructure scales from local workstations to small or moderate scales clusters. You can manage via tools like MPA, RA, and enterprise grade systems orchestrated with Kubernetes without rewriting your core logic. These are things you are going to making use. They're leveraging framework native tools like you can make use of the PyTorch, the Torch Run for lightweight orchestron and production grade solutions. So where you can see that Kubernetes and operators, array clusters, MPI-based workflows. These are all I think you might have come across using these kind of things to automate multi-node coordinations and fault tolerance. You will have to see to that how you are going to automate the things which are running on the different nodes. You'll have to take care of the coordinations between those things, and you'll have to see to that whether they are fault tolerant or not. So evaluate vendor managed platforms such as say you are using, right, you are running some of the things. You will be looking for some of the vendors where you can run your things, right? So AWS SageMaker is Amazon SageMaker, Google Vertex AI, Azure ML, Run AI, Databricks. These are some of the platforms you are able to see as a vendor managed for users. Years of use flexibility and cost trade-offs, ensuring alignment with team size, budget, and scalability needs. Like what's your alignment? Whether you are working on a certain number of people, right? You will be having certain number of employees. What's your budget and what's your scalability need? Based on that, you are going to evaluate the platforms. Okay, what kind of platforms you are looking for? These are some of the examples with respect to the platforms. So by aligning the deployment practices with motivations behind distributed training, speed, scalability, and feasibility. So teams ensure their models train faster and deploy smoother, turning ambitious research into robust production and ready solutions. So this is, you usually see that local environments where you are going to run in a different GPUs, right? Usually you are going to take some workstations, and workstations will be having different GPUs to run your models, to train the model. So in local setups, distributed processing is commonly used to accelerate the training process by maximizing the utilizations of available devices. Okay, what about the available devices? You see this example here. So you have one workstation, and you'll be having different GPUs associated with that, right? So it can be applied to a single machine with multiple GPUs dedicated with the AX stations. If you take it as considered as an NVIDIA DGX station or cloud-based instances. Okay, so you are going to distribute the things with the different GPUs. Okay, the things will run on GPU 0, 1, 2, and 3. So we call it as a multi-GPU machine. So all resources are allocated to a single experiment. Say that you have different GPUs. All the resources will be allocated to a single experiment, what the experiment you are working on. Distributions can be managed by sharing devices within a single process or spanning multiple processes instances. Okay, each assigned to a specific device. So here, utilizing the multiprocessing, is generally preferred, since dedicating a process to each device avoids the performance bottlenecks imposed by a Python JL. So in this context, you will be using the P2P collective span processes are called rank. Okay, each assigned a unique number. Okay, I'm going to give some rank for the processes where rank 0 is typically designed as a master rank and is often tasked with additional responsibilities such as snapshotting or publishing matrices. Like you may have seen that. So in the client server operations also, okay, similar fashion. Okay. And launching experiment in such an environment, you are going to use the PyTorch requires minimal effort, so that you are going to use what are things you are going to use. Okay, using a PyTorch. So after migrating the necessary code, whatever the code you have written, and the remaining steps involve either manually populating the process group initialization parameters, master adder, master port, rank information, and launching the process with the torch multiprocessing function by calling this particular thing, or leveraging the torch run elastic launcher. So in the later part from feature like failure handling automatically sets the required initializations. For that, you can see that this way you are going to handle such things. So the distributed strategies discussed the data model and pipeline parallelism. Okay, so the things are called as the theoretical concepts and practical enables for training and fine tuning some of the today's most impactful models. Okay, usually we are going relying on the multiple GPU setups as we have seen in the previous example NVIDIA DGX, where you have multiple GPUs in a single workstations. So if that is what the size is very small, so that you can make use of the one some of the workstations. So moderate size clusters, where when machine learning models grow too large for single machine, think trillion parameters language models or petabyte scale datasets are there. Your dataset is huge, and the number of parameters generated by such a machine learning model is very huge. The single device may not be able to handle such things. So, okay, in such case, organizations must scale beyond single multi-device nodes. Okay, these cases demand moderate scale clusters so that you may have, for example, you take it as 100 to 10 to 100 nodes locally, or cloud instances, or high performance computing systems to handle the workloads that single nodes cannot process efficiently. So you will be looking for the devices such as high performance devices. For example, training models like GPT-3, so whatever the GPT is now, GPT-5 is explored, right? It requires splitting layers across hundreds of GPUs using tensors and pipeline parallelisms. Like if you say that GPT, the newest GPT, so it is giving most of the features. Okay, so things okay that require to splitting the layers, as well as it will be making use of the several GPUs. Okay, and you are going to making use of the pipeline parallelism as well. Okay, tensor parallelism as well as the pipeline parallelisms you are going to use. At the same time, climate simulations or genomic analysis in scientific domains need clusters to process the massive unstructured data sets. Okay, so you see that if you see some of the things, then they are coming with the massive data set with the different kind of data, such as unstructured data, we say, image, text, audio, video, many things. So to handle such things, you will be relying on certain high performance computing devices. So this is how the moderate size clusters you can see. So if you consider as a HPC cluster here, so you're going to the team, okay, develop the things with the deploying whale launcher and distribute the
Sir,
things.
your
with
screen
the
is not visible, sir.
not visible.
Yeah.
I think I have some network issues. So how long it's not visible?
No, from now only.
No, only have some internet issues. 1 minute. Is there any slides? Some of the slides I'm changing.
Sorry,
Not
sir.
visible at all. Not
No, sir,
visible
no
at all
visible.
now.
No. Your screen is not shared.
Okay, I will. Okay, maybe. Okay, I will share it once again.
Sir, the first session ends by 7:30,
Okay.
and the second session starts by 7:30 itself. So accordingly, you can plan, sir.
Okay, ma'am. Is it visible now?
Yes, sir.
Okay, this current slide is moderate size cluster is visible.
Yeah.
Yeah. Okay. Okay. Shall I stop and continue with the next this one, or what?
No, sir. Just confirm with any doubts with this session, and then.
Yeah. Any doubts, audience, like just going with some flow?
Participants, if you have any doubts, please ask.
Okay. distributed training on moderate size HPC clusters enables the training of previously unmanageable model sizes by launching training jobs on multiple machines. Like you can see that different devices are there. Okay, node 1 to some node n in the one side, and the other side you can see that, and again there's stuff nodes. Okay, the things are being distributed among the different nodes. Okay, it will be running on different nodes, and it will be coming up with the solutions. As I give an example, as the GPT is one of the example where the things are running on different nodes. Okay, different GPU as high performance computing is being used. Okay, similarly the other things like Netflix or your Google kind of thing. So launching distributed jobs in these environments, among others, introduces these considerations where environment management experiments often require dedicated environments, including specific framework, libraries, or device versions. Switching machine environments between the different environments can increases the time between consecutive runs. Okay, so a good approach is to run the workload in centralized environments like Kubernetes, or with scheduling some agents supporting environments, and some pre-unit workflows like array clusters. Okay, there are some of the things can be you can make use to make an environment management. So multi-device job launching, there you can see when the data sets and the models surpasses the capacity of a single machine. Okay, you will have to handle with the multi devices. Okay, you're going to distribute the things with the different devices. Okay, you're going to, they can be distributed across different multiple machines. Okay, the challenge is in interconnecting the process on different devices and ensuring they are synchronized for a specific experiment. Say that you are doing some experiment, but you are distributing your task with the multiple machines. So you are distributing the data as well. Okay, so you will have to sync that, okay, for a specific experiment. That is the one of the challenge. Like here, logs and monitoring, like distributed training across multiple devices. So you will need to look into the monitoring the thing where centralized logging to aggregate process outputs into one location, enabling straightforward examinations and monitoring. And network performance, when the job is distributed over multiple machines rather than all available devices within one host, the network bandwidth interfaces utilization becomes a significant factor in enabling permanent gradient, okay, the exchanges between the different tasks. So moderate clusters are ideal for mid-sized to large teams. Okay, for example, if you say there such as different research labs, startups, or entrepreneurs expanding into AI. So typically you will have to look for how you are going to manage the resources. Okay, whether you are the cloud instances are on premise hardware you are relying on. Collaborations across roles is required. Okay, so data scientists, machine learning engineers, different DevOps being used. Need to balance between the cost and performance to avoid the over provisioning. Okay, for example, your example has been taken by a tech firm analyzing genomic data might use an HPC cluster to run drug discovery day. Simulations alongside the ML workloads. So it's doing the multiple tasks, okay, using the different machine learning. Okay, leveraging the shared infrastructure for both the different tasks. Okay, whatever the task it has been. So it is doing both analyzing the genomic data as well as it is to discovering some drugs. Okay, so using the ML workloads. So examples of how to deploy the distributed machine learning jobs to such a cluster is Elastic Lancer is one of the things where you're going to be making use of the Torch Run is a built-in tool that is designed in a run training jobs across multiple machines. Okay, just making use of to call the command. So that will enable multiple node jobs. Each worker must configure with the consistent environment setup and have the same training code loaded. So that you can see this environment where data scientist is there. So that he is going to call the command. Okay, the things are running on all the different devices. Okay, simultaneously the things will happen by just calling by one call. Okay, as a Torch Run. Okay, launching distributed jobs with the Torch Run that requires loading the training code and running the launch command for each node separately. So as soon as you call, all the nodes will activate, right? Whatever the jobs you have given there. To launch a training job, the torch run command is executed on each worker. Okay, so the command specifies parameters such as number of workers, each worker's rank, the number and addresses for the uh, NGO's endpoint commonly hosted on the master node. Okay, master node is one of the things it is going to take care of. With this, okay, each worker operates within its runtime environment. Whatever the things, okay. So each workers means you have a different nodes. Okay, no node 1, node 0, node 1, node 2 are considered as a different workers for data scientists there. And the auxiliate the logs and metrics into centralized locations requires additional efforts. Okay. So that will involving the master rank or alternative implementations like PyTorch Lightning. So MPI launcher you can make use to launch the run. Okay. So here it will individually launch commands on each node. So it become inefficient and error prone as well. So that you can make use of the MPI interface where it will run. If you call the function, it will work as a master node. Okay. That reduces errors during the deployment. This is an example for that. Okay. That introduces a central entity, the launches that is responsible for starting the jobs and gathering output from the different workers. Okay. As soon as it says that it is launching, and it's also gathering whatever the works is captured, it will be gathering such works. Okay. And it allows flexibility in configuring aspects like transport layer, collectives backend, and fully utilize the supported network capability. So this is the working structure of that, and that has different flavors of launching the job. The most popular ones are over SSH. You can make use of it, or you can over workload schedulers like Slurm or LSF. You can make use. These are the two things. Usually, most popular one is as you use the MPA. So if you run on an MPA job, you're going to mean it should be compatible MPA runtime installed with only the worker nodes requiring the same training code and libraries loaded into the run where you are running in runtime environment. So all this should be available and running it should be there. The launcher node typically does not perform any workload tasks, so it requires minimal resources and does not need the workload specific libraries. Something you can see here. Local rank, word size, and world rank can be given. So Ray is one of the other distributed computing framework designed to simplify the machine learning workflows by as like MPI, abstracting away much of the complexity of the resource management and process coordination. So unlike TorchRun and MPI, it is focuses heavily on static configurations and explicit job launching, but so that it will provide more dynamic and fault tolerant approaches to the distributing training. So Ray train here and trainer will be here, scaling configuration and training functions. Okay, see that launch workers and run the things you say that you can different workers will be there. Okay, so every workers will be having their own training function. You are going to launch through the Ray function. Okay, Ray is a good fit for moderate scale clusters when workflows demand fault tolerances or integration with broader tasks like hyperparameter tuning or distributed processing. That excels the scenarios where the node failures are expected. Okay, so in such case, it is handled. Workloads are dynamic, so that it's like you'll be having different workers will be there. Right? So resources demand vary across the tasks. So large and enterprise clusters will be relying on models and datasets are not only entities that grow and expand. In such cases, we'll have to go with the enterprise environments, organizations often for multiple teams. I think this is how it goes. Okay. We can wind up this session. These are some of the things. Okay. The most likely.
Participants, if you have any doubts, you can ask. We shall move on to the next session.
Any doubts? Okay.
Sir, if required, you can break for some 5 minutes, sir, and we shall start.
Yeah, yeah. If they have any doubts, please we can ask.
Participants, if you have any doubts, please feel free to ask.
Excuse me, sir. Suppose if I run a job on a single machine wherein I have the GPU support, in that
Yeah.
case, can I call it as a distributed one? Will it
Like
stand for a distributed one?
no, you have a single machine, but your workstation has a different GPUs, right?
Huh? Yes.
But if it is running on, you have a different GPUs, it is running on different GPUs, we can call it as a, like, it's single machine, but it is distributed with the different GPUs.
Yes.
The workstation, for example, you purchase the workstation, but the comes with
Oh,
only one
yes.
GPU in the
Yes.
beginning, and later
Yeah.
you can file it up with a different, means more number of GPUs.
Huh,
So the
yes.
data will be running on all the, means if the data is huge, in that case it will be making use of the all such GPUs. So it is distributed.
Okay.
Yeah.
Yes. Thank you, sir.
Yeah. Okay, I'll be back in 1 or 2 minutes.
Yes, sir. Any other doubts? Yes, sir. We shall start after 2 minutes, sir, once you say. Participants, kindly fill the feedback form.
Shall we start, ma'am?
Yeah, sir. We can start. You can share your screen, sir.
Yeah. Okay. We'll start with the automatic machine learning. Okay, AutoML, it stands for automatic machine learning. So like what we have seen that ML, it's similar to that, where we'll discuss some of the things which are
Sir,
aligned with
sorry
that.
to
Yeah,
sorry, sir.
yeah, ma'am.
Sir, please make your screen in slideshow mode, sir. It is not. It is very small.
Okay, yeah, yeah. Is it fine now?
Yeah, sir. Thank you.
Yeah. So automatic machine learning, we call it as AutoML, where we say that automatic machine learning. So what do you mean by automatic machine learning? Okay, that says that uh, you are going to make the process automated, right? So for example, that is what the basic concept. Okay, it is a process of automating the time-consuming related tasks of machine learning model development, right? You want to make it as automated. I mean, you want to say that you don't want to spend most of the time with that. What we have discussed already, some of the things. It allows data scientists, analysts, and developers to build ML models with large scale efficiency and productivity, all while sustaining the model quality. There you say that what are the things are involving. So, for example, if you see manual model development, usually how the pipeline will look like. Okay, manual model development or traditional model development look like. So you will be having whatever the things we have already discussed in the last in this one session. So mainly we'll be relying on the data collections and data preprocessing. So initially will be you will have to collect the data collection, data cleaning, and data aggregation or data augmentations. These are the things will come into the picture first, right? Once you collect the data, so we'll have to do some data labeling, right? Data labeling will be taken some of the time, and you'll be moving on to feature engineering while developing the model. Okay, model development will be having some of the things. Okay, where feature engineering will be there. Okay, where you can see that you can call it as a meta learning or feature extraction, or you can say that feature selection. Okay, that's several algorithms we have already experienced. Right? So that we will have to select certain features, or we have to extract some features. We are going to use certain models to do such tasks for us. Okay, feature engineering itself requires some machine learning models there, and you are going to use such machine learning models, and we go with the model selection or model development, okay, so that we can see that what kind of machine learning algorithms or deep learning algorithms we are going to make use. Say, for example, it can be SVM, decision tree, random forest, or naive Bayes, okay, whatever it can be. So I want to select some things, and then you have to select some hyperparameters. We call it as the hyperparameter tuning or hyperparameter optimizations. Okay, so there are several hyperparameters are available with this. So you'll see to that whether it can be random search or grid search, Bayesian optimizations. There are several other hyperparameters optimizations that are available to evaluate the model. Okay, so finally, after all these things, we will come up with the some machine learning model, or the model will be developed. So means once it is developed to deploy the thing. So automatic machine learning. That you imagine you are, for example, why that the automatic machine learning is required. Okay, they require that you are a coach on a team. Okay, you are in the marketing department for a digital retailer, or you are working on an architectural project that is identifying types of building. Okay. Your business has in contact from on its website. These are some of the things you are seeing that. Okay, so you'll have to do some. For example, if you want to do something in such a any one of these things, you will have to manually curating the videos. So that we'll have to see to that. What are the different things are available? The images, tables. Okay, it's tedious and time consuming as well. You have to do all things manually. so that if you come up with something, okay, automatically can be done for you for your task, so that you wanted to see, for nowadays we have things, okay, so CCTV cameras, okay, wanted to earlier days you will have to see that particular video, okay, something went wrong, you have to go to that particular some of the locations, some of the frames, you have to figure it out manually, have to do that, right? So nowadays, the thing comes automated, so that if you feed the video to a certain model, that model will come up with some solutions for you. So it will test the job for you, right? It automatically will bring you some information. That's what automated things. Okay, such things can be used and such things can be deployed. Such models can be deployed to the whatever the example I have given as the traffic management. Okay, in the traffic signals. Then the traffic signals, the camera being kept, okay, such machines, okay, those machines are able to do such stuff. That's what that some things can be done on behalf of you. So automatically they are going to identify and that will flag the content. So for example, the foreign object has come, okay, it will be triggering for you, say that foreign object has come. Recently I have seen on video it, okay, the cheetah used to come to your home, okay, you may be in city, or you may be some near to the Bannerghatta place in Bengaluru. So there the cheetahs may come into your home. So that you have a camera, so you have kept a camera in your CCTV camera. The CCTV camera can recognize somebody is coming. Okay, it's recognizing it is giving you some trigger for you. Okay, some beep sound or something. Okay, how benefit for you are, right? So such things where the automatic machine learning things used to come to do such automated things. This is one of the example. So the whole process can be called as an automated process. Okay. So we call it as an auto ML. Okay. So as we have seen in the previous one is the manual ML, manually how you have to develop the model. So you can develop the model as in automatically. Okay. So again here you're going to see to that all these process can be done on behalf of you, so that it does the data labeling. Okay, data labeling. There are several applications are available, so that you are going to call the API. Okay, that does the job for you. Whatever the data you are going to feed, it is going to do the data labeling for you, and whatever the data labeling applications, whatever the things are available, it does the feature engineering for you. It will select what are the features is important for you. For example, if you go to the main difference between machine learning and deep learning, if you see, deep learning will select the features on its own. Welcome to the machine learning. Most of the cases, you have to select the features, right? Based on the applications, whatever applications you are going to develop. Usually in the machine learning, you are going to select features. Okay, same way, the AutoML, where the feature engineering is done by your machine itself. It is selecting the features for on behalf of you. It select based on whatever the application means. You come up with certain algorithm that give you the best features for you, and you're going to select a model instead of you do trial and error. The thing it will only suggest you these are the algorithm is suit for your applications, right? And it will only select you some parameters. Okay, it can be anything, so that you are going to get the result at the end. Okay, this is how the automated machine learning can use. And okay, so automatic machine learning, tuning matters. Okay, the whatever the tuning you wanted to do, that matters a lot. Okay, for example, if you say that training data is there, feature selection, you wanted to select some features. Okay, so then whatever the features you've selected, and that should be more accurate. Okay, so that will have to be more relevant features for your task. Okay, so that you are going to see that number of features selected. Okay, you are going to evaluate in some manner. Okay, based on that whatever the score you get, and you are going to say if this is the score, so and so score, I'm going to make use of this particular thing on my work. And you are going to select some machine learning algorithms, so that based on the more the features, uh, more the relevant features, the better the performance of the model. Okay. So like that, you are going to do, you will have to fine tune the model. So, and it requires huge tuning spaces. Okay. Yes. Why it requires the huge tuning spaces means it will be looking for every possibility. So you are doing on your own, like you will be doing some trial and error, and you are going to select some of them. But while coming to automated machine learning thing, it has to look into the different cases. Okay, you have fed the data, so it has to come up with the model, so that model say that it is automatically labeling for you. So it requires large space to do that. For example, to do the data pre-processing, okay, it requires say that 20 plus components are available. How you are going to how the machine learning automatically how you are going to come up with certain features or certain pre-processing can be done, right? It requires more space. Okay? So that in such sense, we call it as a huge tuning page spaces are required to do certain tasks. Okay. So if you take it as an example, I've taken most of the sites I've taken from some online sources. Uh, Motivation is success of the deep learning. So if you see the deep learning examples, whatever in speech recognition or computer vision or reasoning in games. Okay. So how does it work usually? It works. For example, if you take it as speech recognition, you are speaking in Kannada, it will be replying in Kannada. For example, if you say some of the applications, if you go to the Google, usually the Google Assistant, you are going to ask something in Kannada, usually you may get a reply back in certain language, right? Usually, most of the people are interacting with the English. So there are other languages that are available. Most of the people are working on that. And computer vision in self-driving cars. So it will how does it work? The self-driving car. So it does the things. It's going to most of the places like it's going to identify. Say, for example, if there's some obstacle is there, it's going to recognize. For that, you will be having success. So you have certain sensors. That action has to be taken by your device that is already deployed in that. Right. So either you may have the back camera, front camera. The number of sensors being kept on that, right? That does on its own, right? The means you say that self-driving cars, it's running on its own. No, nobody is there to monitor for you, right? And reasoning in games, okay, these are some of the examples. Okay. These sensors made think about the means automated machine learning. Such things can be done, right? So one problem of deep learning is that performance is very sensitive to the whatever the hyperparameters you are going to choose, where we don't have any control on the hyperparameters, what the hyperparameters we wanted to choose on behalf of means whatever the deep learning models you want to do. So, for example, if you wanted to select the learning rate, we don't have the say that this is the learning rate I'm going to use. Right? We are not aware of which learning rate will suit for us and which optimization algorithm will suit for our this one, which momentum, what is the amount of momentum we have to give during training, what normalizations I should go ahead with, what is the batch sizes I can select, what is the dropout rates, what should be the weight decay, and what are the different data augmentations. Okay, what is the number of epochs I have to use? Okay, what is the loss function I have to use? Okay, these are all different hyperparameters uh, are employing in the deep learning model, but we don't have any certain standard algorithms to say that you pick these so and so things so that you will get a good accuracy or you will get a fruitful result, right? So things are not available, right? That is one of the major means again the deep learning model is more sensitive with these kind of parameters. If any of the one of the parameters is doing something wrong, then you may not get a fruitful result. So okay, so mainly your architectural hyperparameters are the things one which is morely deep learning models are relying on. So deep learning and auto ML, if you see that current deep learning practices, how they work is you expert chooses the architecture and hyperparameters. Usually, for example, you are developing a model. You will going to choose some architecture, okay, based on your experience, based on the literature you have conducted. Okay. So you will feel that this architecture will work for your task. Okay. So for example, if you go with the image things, you may see that certain transfer learning models will help for you. you will stick to that, and you are going to change some certain parameters, set of parameters. Okay. And it will be developing a model, and based on the results, you are going to change your architecture or your hyperparameters. So it is a cycle, will happen for a number of times. So until you get a certain result, usually it happens. So AutoML will be, it is a true end-to-end learning. Okay. So where you are going to use the middle level learning and optimizations, and learning box will be there. So where the meta learning will be happening. So you will, right start from the data collections. Okay, whatever the data collection or data preparation, you will be relying on. Okay, whether do you have enough data, or whether there is any existing data sets are available, or data in the data collections you are going to look for data stretching, data searching, or data you will look for a data synthesis. Okay, based on that, okay, you if you have enough data, otherwise you will have to do some certain things to do enhance the data set, either synthesizing the data set or augmenting the data, and then you will look for the data quality and data cleaning, right? Data recommendations and model training will be happening. So all such things, okay, that does, okay, uh, on its own, and it does the optimizations for you, and it will come up with the model. Okay, your involvement or whatever the human involvement will be less in that case. So the what is the vision of the automatic machine learning is AutoML allows non-experts to make use of machine learning models and techniques. You don't need to be an expert to choose what algorithms I want to choose. Whether I can go with HPM or random forest or decision tree or logistic regression, whatever. Okay, it doesn't require any such expertise to say that. Okay, so it will take a trial and error basis. It does something, and it's come up with the certain algorithms for you, okay, based on some of the experiments. On its own, it does that. And what the scope is, automate data processing. So you don't need to do whatever the things we have discussed so far, whether you are having enough data, or whether you need to do some synthesize the data, or you want to do some augmenting the data, or data is having some, whether the data is quality or data is having some problem, all such things. Okay, it doesn't matter. Okay? So it does feature engineering, data pre-processing, okay, and selecting some hyperparameters, okay, and selecting some learning model, okay, on its own, right? Trying the data with the target place with the different metrics. Okay, AutoML will does the job for you. The survival job saying that data pre-processing, features generalization selections. Okay, the other things can be done. You will come up with some model at the end. Okay, that will be more accurate, better than the other expert come up with. Okay, that's what most of the things. Okay, you may have experience with low code, no code concept has already arrived. Okay, so the person cannot be an expert with the machine learning model. He can make use of such model, such things, right? Earlier days, you should, for example, if you go, okay, that example is not okay. Learning box is not restricted to deep learning here. So traditional machine learning pipeline will be look like this. As we have seen already, clean and process, select, engineer, better features, select a model family. The thing. So how does it ML work? Okay, as we have seen that already, it takes some user inputs. It can be data or data metric or constraints. Okay, these are all some of the inputs being given from the user. Say that I am going to feed some data, and I'm going to see that these are the target metric I'm going to use, and these are some of the constraints I want to relying on the time or cost. Okay, I think such constraints is been given. Based on those constraints, the automatic machine learning will do some iterations with the different features, different algorithm, different parameters, and it is going to check with the what is the score it is going to obtain. Okay, in the first iteration it may get 50%, second iteration it got 76%, 53% in the third iteration, fourth iteration it kind of 25%, something like that it has got. So later it is going to prepare a leaderboard. So it's saying that what is the rank and what is the model. Okay, it means it says that these are the features, these are the combinations of the features, parameters, and algorithms. For these are the combinations, I'm going to get so and so percentage in the 10 scores. So in this example, you can say that 95% is one score, 76% is another score, 53% is another score. Based on this, you're going to select some of the model for you, right? Which So the top model you may see that this model is good for you. That's how does it work. So it has 3 steps. Okay, search space. Okay, that look for the domain knowledge. As I told you that it starts from the right from the data. And search strategy, what is the strategy you are going to make use to do the task for you. Okay, say that and pipeline you are going to use performance estimate of P, performance estimate for a certain strategy. Okay, so it is a cycle. It does, okay, whether some strategies are not there, you are going to include those things for several number of times. It does the job. Okay, and hyperparameter optimization. These are some of things you are going to see. Hyperparameter optimizations, neural architecture search. Okay, what architecture you wanted to see, and what are the hyperparameters? How does it go with the optimizing the hyperparameters, and what is the meta learning can be done? Okay. So here you can see hyperparameter optimizations. Okay, the definition says that if you say let lambda be the hyperparameters of the ML algorithm, so A is an algorithm here with domain some model called lambda. So you're going to call the function L of a lambda, means you're going to say that the lambda is an domain. What domain? For example, it can be healthcare domain, or it can be IoT domain, or it can be agriculture domain, or it can be what is that speech domain, or it can be text, okay, natural language processing domain, whatever the domain. Okay, so A is the algorithm and lambda is the domain, and you have a data, train data and validated data, so that D train and D valid. So and that denotes the loss of A. Okay, so the loss you are going to say this based on these other things. Okay, what is the algorithm, what is the trained data, and what is the validated data? You are going to get some loss for a certain algorithm called A. So using the parameters called some parameters. Okay, so train on D train and evaluated on the D valid. Data train data set will of train data set and data validation data set. The hyperparameters optimizations problem is to find hyperparameter configurations lambda star that minimizes this loss, whatever the loss you are going to see. In the previous slide, you might have seen that. So this is how we are going to see the top scores. Okay. So it has to find the loss here. Okay, the loss we need to minimize. Okay, in typical machine learning models, you and deep learning models, you might have seen that. Okay, you are going to global minima, local minima, and the gradient descent, so that you will have to achieve the global minima. So similar way, you will have to find the loss has to be very minimized. Okay, for a certain hyperparameters you are going to choose. It is mostly working on hyperparameter optimization. Okay, so what are the hyperparameters are suitable for your certain task? It is Solent job is to find certain hyperparameters. As we have seen that what are the hyperparameters? Okay, learning rate optimization, Adam optimizer, epochs, okay, something like that. See here, what are the types of hyperparameters we are going to use? Like continuous, if it is continuous hyperparameters, then you say that example is the learning rate. Okay. So if it is an integer hyperparameters, you can take an example as the number of units in that, number of epochs in this. Right. And if you say the categorical, then finite domain, unordered, you can take an example as the algorithm is one of the things. We are going to select some algorithm. It can be SVM, random forest, neural network, what is that? any other decision tree, right? Something like that. Any algorithm. Okay. And another example is the activation functions. You want to select certain activation functions, which activation function which will work for my hidden layer. Okay. It can be should I go with the ReLU, leaky ReLU or TANH. Okay. These are some of the algorithms. Sorry, activation functions. Which one is relying on? Example 3 is operator. Okay. Which kernel size I should go with? Which pooling strategy I should relying on? These are the things you can think. Okay, special cases like binary, you can either 0 or 1, you are going to select. Okay, these are some of the types of hyperparameters you are going to see. So conditional hyperparameters. So say that conditional hyperparameters B are only active if other hyperparameters A are set a certain way. So you will be having, say that I wanted to go with the certain momentum based on my learning rate, or based on error I'm going to error and loss, I will have to go with the certain optimizers. Okay, these are some of the certain conditions. Say that, right? So example one says that A, you are going to say that, okay, hyperparameter A, choice of optimizers, either Adam or SGD. So you're going to select the things as Adam's second momentum hyperparameter, only active if A is equal to Adam. Right? That's how you are going to select them. It is how the conditional hyperparameters are. Example 2 is if it is a is a type of layer, you say that convolution, max pooling are fully connected. So B says that convolution kernel sizes of that particular layer only active if A is equal to convolution. Right? Which one you are relying on? Whether you want to convolution, max pooling, or fully connected? So the kernel size will be active only when you say that A is equal to is of convolution operations. That's what true, right? If you're generating some deep learning model, so you're going to say that you wanted to go with the kernel, then there should be a convolution supposed to be happen prior to that. Okay? So, based on the convolution, you're going to apply kernel certain kernel size for that. So it has to match, right? Your kernel size you are going to choose based on the values on the means whether it is going to fit for certain convolution or not. For example, if you take the example as 7 cross 7 as the convolution, means you have an input thing, and you go with the convolution with the 3 cross 3, 3 cross 3 with the stride as 3. Okay, in such case, it will not match. Yes or no? So if you say to that, you cannot go with the straight as 3 with the 7 cross 7 as an image size, and you are going to give what is that kernel size as 3 and straight as 3. It will not work. So it needs a padding in that case. Okay, it will not match. It is not able to generate a feature match. Okay, in such case, it is depending, right? It's depending on the what kind of this kernel size and the stride. So it will be either accepting or rejecting. Okay? In that case, it is rejecting. Okay? It will has to modify the stride as either 2 or 1. Okay? In that case, only it will work. Like that, it is going to give some suggestions and it is going to update. And example 3 is a choice of classifier and random forest or SVM. Okay, it's going to say that which algorithm you are going to use a random forest or SVM. So SVM kernel parameters only active if A is equal to SVM. Means you say that SVM kernel parameters you are going to use, so that it has to select only if that is of SVM. Right? Sorry. Oh yeah, A is equal to SVM. Okay, that's what we discussed. AutoML as hyperparameter optimization. In the case, combined algorithm selection and hyperparameter optimization. We call it as a cache here. So if you say let A is equal to, you have some set of algorithms, as we have seen in the previous case, say that if you see here, you can see that algorithms SVM, random forest, and neural network in the example 1. The same thing is taken here. A is equal to certain algorithms, A1 to AN, be a set of algorithms, and you're going to say that certain hyperparameters, you're going to select lambda is a hyperparameter. Space of AI for 1 I is equal to 1 to n. Okay, there are several hyperparameters variable. You have kept to say, and loss function, you're going to check with the loss of AI using lambda. It belongs to the capital lambda. Okay, whatever the hyperparameters you're going to use. Okay, set of hyperparameters trained on certain data set, trained data set, and testing data set. You're going to evaluate with the data, come up with the loss. So the combined algorithm selection and parameter optimization problem is to find the combinations of algorithm and hyperparameter configuration that minimizes the loss. Okay. As we have seen in the previously one of the slides saying that the rank of the certain percentage, you're going to order it with respect to 95%, 73%, 40, 56% kind of thing. There, it does for certain algorithms with the certain parameters. Okay, group of combinations of different algorithms and combinations of different hyperparameters. It does all such things. It kind of the Cartesian product of the thing. Right? So it should minimize the loss. Okay, whoever is having the lesser the loss, that particular group is considered as the better. Better algorithm. Okay, simply hyperparameter. Sorry, what is that? Hyperparameter optimization problem with the top level hyperparameters choice of algorithm. That all other hyperparameters are conditional. That's what it is. So that if you take it in Auto Veka as an example, 760 hyperparameters with a 4 level of conditionality is going to use. So the black box hyperparameter optimization. So what I mean by black box hyperparameter optimizations, like, so here you are you will have to you're not aware of what kind of hyperparameters is happening there, right? Deep learning hyperparameter setting is the lambda one, and you will be having some black box optimizers. Okay, that is going to take the function of f of lambda is equal to lambda, and validation performance is happening with the f of lambda there. Lambda is the function lambda is going to take the input as different hyperparameters. So the set of hyperparameters. The black box function is expensive to evaluate. That is, sample efficiency is not important in that case. Say to that. Okay. So in that case, you will go with the concept called grid search and model search. Okay, grid search is the most basic method of the hyperparameter optimization method. That is also called as full factorial design. Means why we call it as a full factorial design means it is going to do some Cartesian the Cartesian product of all the possible things. Okay, it does many computations, many combinations it has to check. Okay, here the user specifies the final set of values for each hyperparameter. Say that these are the hyperparameters I'm looking for: running rate, epoch, or what is that dropout layer, many things. Okay, and the way the grid search evaluates what I said, that the Cartesian product of whatever the hyperparameters you set, and there it is suffering from the curse of the dimensionality. Why? Because the required number of functions evaluations that grows exponentially with the dimensionality of the configuration space. Since you are going with the Cartesian product of the different sets, obviously it is automatically the number of evaluations will grows exponentially. Okay. And also it increases the resolutions of the discretizations, substantiability of the increasing the required number of functions evaluations. Okay, so these are the some of the problems with the grid search. Okay, both and random. The next one is the random search, where random search it is going to select randomly some of those things. Okay, until it reaches some certain budget for the search. Okay, so that you are going to say that this is the threshold to do that. Okay, until the threshold is been reached, so that you are going to do some randomly it is going to select, it is going to take this combinations of the things. But in case of the grid search, it is going to do Cartesian product of all the hyperparameters of available in that, and it is going to check for all the means it's going to check the result for all those things. So assume that there are 10 hyperparameters are there, means it has to 10 into 10 means it has to do some 100 such computations, right? After doing some 100 such combinations of computations, then only it is going to select some. But while coming to the random, this one, it is not in that case. It works better as compared to the grid search. Okay, there the number it is going to select randomly, and the number of hyperparameters are available for the grid search is more as compared to the number of hyperparameters for the required for the random search is less. Okay, and the grid search includes okay, to do parallelizations, okay, and flexible resource allocations where you random search is better. Okay, so that's what it sees here. Both completely uniform random search handles unimportant dimensions better, and random search is useful as the baseline as compared to grid search. And the next one is Bayesian optimizations approach you are going to use, so that we have seen that some of the things. Okay, that optimizations is a state-of-the-art optimizations where the framework for a global optimization uh, of expensive black box functions. Okay, and here the Bayesian optimizations approach it presents the means if there are two things. One is the Bayesian optimizations and surrogate model to be used. It is an alternate for the surrogate models being used, and it's an iterative approach with the two key ingredients where it's going to use the probabilistic surrogate model and acquisition functions to decide uh, which point to evaluate text. Okay, that's what the approach is, to fit probabilistic model to the function evaluations. That is what lambda comma f of lambda, and use that model to trade off with the explorations versus AI exploitations. And it is simple and efficient. Works when objective is non-convex, noisy, and has unknown derivatives. Okay. Recent convergence results. Okay, so it depending on observations. Okay, and means mainly will be working with the acquisition functions. What it does. Okay, and problems for standard Gaussian process approach. Okay. With respect to Bayesian, the challenges associated with the Bayesian optimizations. Okay. The complex hyperparameter space. Okay. So the things are high dimensional, low effective dimensionality, mixed continuous or discrete hyperparameters, conditional hyperparameters, what you have seen. Okay. So they are conditional with the whatever the hyperparameters is already been selected. Okay. So I want to take some set of algorithms. It is based on certain things we have seen in the previous some of the examples. Okay, and mixed continuous or discrete hyperparameters. Okay, so sometimes they may not match high dimensional and low effective dimensionality. So if we have a noise, sometimes heterozygotic large non-Gaussian robustness. Okay, using model is like overhead. So budget is runtime, not number of functions or evaluation. Okay. These are some of the problems for standard Gaussian process approach. And simple solutions usually SMAC. SMAC is one of the framework or a tool to do the certain things here. Okay. So mainly your goal is to minimize the loss, right? So you can SMAC is going to give you some solutions. For example, it is a random forest. Okay, frequency uncertainty estimate, variance across individual trees, predictions, etc. And two recent promising models for Bayesian optimizations are neural network with Bayesian linear regression, using the features in the output layer. Okay, fully Bayesian neural networks trained with the stochastic gradient like Hamilton, Monte Carlo thing. So what we are seeing that Gaussian process, usually it is going to use the function where you're going to call the function with the model with the lambda as hyperparameters, and you're going to select some of the hyperparameters. It is fully specified by the mean of the value, and the covariance functions you are going to use different kernels, and the mean functions is usually assumed to be the constant in the Bayesian optimization cases. And Gaussian process by using only a subset of the original dataset as inducing points in the building the kernel matrix, whatever the kernel matrix you want to use. And here you will have to see that it is going to strong performance on the low dimensionals with respect to the hyperparameter optimizations library task. Okay, so that it will be means high dimensionality conditional hyperparameters are the thing going to be used. So tree of Poisson estimators are some of the things. Before that, some of the available tools are like SMAC, one of the frameworks is being used in Bayesian optimization, and it's going to use some certain algorithms to enable the prominent frameworks. Okay, so some of the available frameworks as AutoVeka, Scikit-learn are some of the available frameworks with respect to the AutoML. So here, the tree of Poisson estimators is an estimator for conditional hyperparameters. Okay, so as we have discussed, okay, if you say that it is a conditional hyperparameter, this is one of the estimator that will help you to choose for the conditional hyperparameters, and it will demonstrate for good performance on for hyperparameter optimizations. So here it does non-parametric KDs for probability of A lambda is good or lambda is bad, rather than it's going to say that probability of Y given certain number of parameters. Okay. So you are going to say that the model Y for certain number of hyperparameters has been chosen. So it is equivalent to expected improvement. Okay, the pros for this efficient. Okay, the thing is complexity is go up N into D, and it is parallelizable and it is robust. The disadvantage is less sample efficient than Gaussian process. So some of the things are population-based methods. Okay, there we can see the populations of configurations, maintain diversity, improve fitness of the populations, and evolutionary strategies. These are some of the examples for that. Very competitive for a few of deep learning neural networks, and embracing parallel and parallel purely continuous. So modern hyperparameter optimizations. So beyond black box hyperparameter optimizations are DNN hyperparameter. This means they are too slow for deep learning or big data. Since they are looking for all the possible options. Okay. So next is hyperparameter with the gradient descent. Say that formulations as bi-level optimizations problem. So there you are going to minimize the loss. So you are going to associate it with the weight. Okay, for parameters you are going to use hyperparameter, so that the weight is you're going to weight of a certain hyperparameters. You're going to take the minimum weight means with respect to the loss during the train with respect to the weight and hyperparameter. That's what that particular formula says. Derived through the entire optimization process, and iterative optimization steps being used. Say that hyperparameter gradient step with respect to the gradient is being used with respect to the validation loss, and parameter gradient step with respect to the gradient with respect to the weight of the loss associated with the train. And probably extrapolation of the learning curves, okay, parametric curves over the models and Bayesian neural networks. So next is multi-fidelity optimizations. Means how you're going to optimize the hyperparameters using the multi-fidelity optimization. So data set sizes are increasing, means keep on increasing, and increasing the complex model is it is one of the major hurdles for the hyperparameter optimizations. Say that the data set is also keep on increasing, and that increases the complexity of the model as well. So means the number of trainable parameters are also keep on increasing as soon as the number of data set and the complexity of images are complexity of the data is increasing. Right, and if you are using the making use of black box, okay, that again, okay, it does the thing that is also considered as the expensive thing. Okay, so training a single hyperparameter configurations on large different data sets can it is easy that exists like in terms of the time taken by the learning model. And a common technique to speed up the manual tuning is on mainly relying on the algorithm and hyperparameters is being going to use. Okay, so you have to relying on small subset of the data, and you're going to train the model, and based on the output you're going to get, you are going to train the model with some number of data. For example, we have 1,000 number of images are there, so you're going to train the model with the 100 number of images, and instead of going with 100 number of epochs, you may go with some 10 number of epochs, and you're going to do certain things with a different subset of that to get a certain features to visualize that. Okay. So you can do some certain tasks. Okay, so you can do some downsampling as I told you, that number of images. Okay, so multi-fidelity is going to catch such manual problems. Okay, into formal algorithms using fidelity approximations for the actual loss function to minimize the actual, means whatever the loss you are going to encounter through that. Okay, so and that approximates the trade-off between the optimization performance and the runtime. So that is going to done by the multi-fidelity optimizations. Okay, mainly with that. Okay, and so in that case, you will have to see to that which model and algorithm learning curve during training and can stop training procedures. Okay, so that how the learning curve is going to, we are able to see during the training based on certain number of algorithms, and then you have to see to that certain methods. You have to select certain algorithms, certain parameters based on that curve you are going to see. Okay, and then you have to discuss with the multi-fidelity methods, which can accurately decide which fidelity will provide most information, like about finding the optimal hyperparameter, which hyperparameters are useful for dominating for your particular task. Okay, so the things you are going to do as first you are going to see to that how the learning curve we are going to see for certain algorithms, and then you will be analyzing with the number of hyperparameters combinations, and then you are going to decide which is better for that. Okay, so it is subsets of the data, means as I told you that you are going to take the subset of the data and you are going to do it with the number of epochs of iterative training algorithms, and with respect to and shorter MCMC chains in Bayesian deep learning, fewer trials in deep performance learning, downsampling images in the object recognition. These are the things, some of the things you are going to do. Also applicable in different domains, okay, such as fluid simulations, less particles, shorter simulations, kind of thing. And subsets of the data, as you have seen, see what kind of loss you are going to see. Okay, size of subset of MNIST data. Many cheap evaluations on small subsets, few expensive evaluations on the full data. You can see if you are going to use. Okay, cheap evaluations on can do with a small set of data set. If you are going to making use of the full data, then you will be using the expensive evaluations. That's it, a Gaussian process model, saying the type of the function with respect to the number of whatever the hyperparameters being used to predict performance as a function of hyperparameters lambda and the budget b. So it chooses both lambda, whatever the hyperparameters, and the budget b to maximize the bang for the buck. Like it's going to maximize, means minimizing the actual loss in that case. So this is how the simpler approach recursive halving, like validation accuracy, based on the time it's going to take to means what is the time encountered for that. This will not go much. Bayesian optimizations and hyperband. So advantages of the hyperband is hyperband is a hedging strategy that is designed to combat the problem when selecting some randomly sampled configurations, what we have seen in the previous case. It is, instead of going to do that, it is going to divide total budget into several combinations of the number of configurations, okay, with respect to the budget, and then it calls the successive halving as a subroutine on each set of the whatever the random configurations you have choose. Okay, due to that, means it maximizes the budget in the worst cases and minimizes the loss. Okay, so advantages of this is strong anytime performance, general purpose, such as low dimensional continuous space, high dimensional continuous spaces with conditionality, categorical dimension, and easy to implement and scalable, and easily it's parallelizable. And advantages of Bayesian optimizations is strong and final performance, combining the best of both worlds in case of Bayesian optimizations and hyperbanding. Bayesian optimizations for choosing the configuration to evaluate, and hyperband is for deciding how to allocate the budgets. You can combine. You can you're going to take the advantages of the both here, which is based on what concept. Say that Bayesian optimizations is for one task and hyperband is for the other one. And if you go with hyperband versus random search, the advantage is improved anytime the performance. The loss you're going to keep on decreasing. See, after optimizations with this and combine the Bayesian optimizations and hyperband, you're able to see strong anytime and final performance. Means you're going to see the what is that loss is minimal. Okay, this is how the things work with. And hyperparameters optimizations for practice, which tool to use. Okay, what are the tools you recommended to use? Say that if you have access to multiple fidelities, so it has been recommended that combinations of those two. Okay, what is that Bayesian optimizations and hyperband, and combines with the advantages of the TP and hyperband. And if you don't have access to the multiple fidelities, then you can go with the low dimension continuous, such as Gaussian process-based basic optimization, and high dimensional categorical and conditional, such as MAC or TP, and purely continuous. The budget is in terms of multiples of 10. In such case, means greater than multiples of 10 of the dimensionality, then you can go with the same AVS. These are some of the things. Okay, open source AutoML tools based on HPU, like hyperparameter optimizations are AutoWeka. It has 760 hyperparameters, 4 levels of conditionality based on Weka and SMAC. Okay, hyper of scikit-learn based on scikit-learn and TP. Auto scikit-learn based on scikit-learn and SMAC what is that? Bayesian optimization and hyperband. Uses meta learning and post-hoc ensembling, and topped based on scikit-learn and evolutionary algorithms. And HTU and AutoML is based on the random search and stacking. These are some of the open source AutoML tools which are available. And AutoML democratizations of the machine learning is Auto scikit-learn also won the last two phases of the AutoML challenge is being performed. It performed better than the 130 teams like it's during the challenge. So neural architectural searches. So here the chain structure space is being used. Okay, the input is like input to the next level is the previous layer. Output will be the like what we see in our model. Okay. So input is usually input is will be given for the what is the thing layer. Okay, L0. Okay, L1 will be depending on L0, and L minus 1 is depending on L minus 2 or something like that. Okay, so it can be say that it receives the input from the previous layer. Okay, and output the output of the certain layer will be the input to the next layer. Okay, that is what how the algorithm comes. Okay, then the search spaces here is then it is parameterized one. Okay, the maximum number of layers. Okay, the means the maximum the number of layers, the possibly the unbounded, and the type of operations every layer can execute, And pooling convolutions are more advanced layer types. Okay, you can say that you can make use of the depth-wise separable convolutions or dilated convolutions. Okay, and you can say that hyperparameters associated with the different operations. Okay, it can be number of whatever filters are available, strides, padding, okay, and convolution layers, and fully connected networks, and parameterizations is happens of the search space is not fixed aligned, okay, conditional, which is depending on the conditional space. Okay, in the other case, it has some keep connections, what we have seen in generally in our some of the deep learning models like RNN. Okay, they follow some connections. Okay, so the same things is being used. Okay, which allow to build the complex more things using multi-branch network. Okay, by using the keep connection. See that L3 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 is having multi-branch, so that's L4 and L5. So L4 is getting the different inputs from L2 and L3. Okay, and L8 is it is through the skip connection from the L0 to L8 and getting from the L6. Okay, this is how we say that. That is what considered as special cases of these are multi-branch architecture or the chain structure network being used here. So as I told you, some of the examples, right, the residual networks, okay, RNN, dense nets, okay, which are the things they use this kind of architecture. So that optimizes the two different kinds of cells, saying that normal cell and reduction cells been used to do that. So advantages are like the size of the surface is drastically reduced since cells can be comparably small, and cells can more easily to transform to the other datasets by adapting the number of cells used within the model. This is how the network architectural space you are going to look into. Okay, so different architectural space you want to select, right? Select one hidden state. You see this in this example. Okay, second hidden state. Okay, select operations for the first hidden state and second operations for the second hidden state, something like that. So 5 categorical choices for the n block. So you see here 2 categorical choices of hidden states, each with domain, and 2 categorical choices for some of the operations, 1 categorical choice for the combinations. So that total number of parameters for cell. So unrestricted search spaces are possible with conditional parameters, but only by 2 pre-specified maximum number of layers. The examples are chain structures search space, what we have seen in the previous example, like previous slide. Top level hyperparameters, number of layers L, and hyperparameters of layer K, conditional on L is greater than or equal to K. That's what we have seen in this one example. Okay. So reinforcement learning, what we have means most of the things are automated through the reinforcement learning. So network architecture space with reinforcement learning is the state-of-the-art results for say for 10 tree bank, large computational demands. Nowadays, whatever the GPTs are being, they're also making use of the same. So 800 GPUs for 3 to 4 weeks, 12.800 architectures are being evaluated. So you can see here the controller of the RNN. It is sample architecture A with probability P, trains a chain network with architecture A to get accuracy R, and then you are going to compute the gradient of P and scale it by R to update the controller. It is cycle, like it's going to take the feedback and it is going to update the things as like a general one. Next is neuro evaluation. Evaluation is nothing. Neuro evaluation typically optimizes both architecture and weights with the evolutionary model. And mutation steps such as adding, changing, or removing a layer. So based on you are going to we have seen from the last history how it has been evolved. Okay, neural network is been evolved. It's called neuro evolution. So you're going to add the steps, or you want to add, like changing or removing the layer. So the skip connection is like you are going to just to skip some of the connections, right? Something like that. So regularized are using the evaluations, standard evaluation algorithms, but oldest solutions are dropped from the populations. So you are going to see to that state of the art results based on say certain image fixed length cells are such pieces are being used. Okay, you are going to compare comparison of the evaluations of the RL and random search. Okay, this is how the comparison is made with the top test accuracy sign experiment with the number of hours. And Bayesian optimizations, okay, joint optimizations of a vision architecture with 238 hyperparameters with the TPE. And AutoNet kernels for GP-based NAS and equation models-based optimizations. These are some of the Bayesian optimizations. Joint architecture and hyperparameter search with SMAC with respect to the AutoNet. And first auto deep learning system to win a competition status set against a human expert. Kernels for GP-based NAS are ARC kernel and NASBot. Sequential model-based optimizations are PNAS. And main approaches for making NAS efficient is weight inheritance and network morphisms, weight sharing and one-shot models, multi-fidelity optimizations and meta learning. Network morphisms, like you're going to make use one model has been developed and you're going to make it for the different things, right? Changing the network structure but not the model and function. You're going to just to change model function is same, but you're going to change only the structure of the network. But it finally means it does the functionality is most same, right? Like polymorphism, what we say in your programming language. Similar way, network morphism. Okay. So that is for every input, the network yields the same output. Okay, as before applying the network morphism. That allows the efficient moves in the network space. What is the network space you are going to select? Weight inheritance and network morphisms, you are going to inherit the weight. Okay, as like inheritance, apply network morphism, okay, different models, and you are going to train in certain sequences, and you are going to get the update the models, which model is the best model. Okay, enables efficient architecture search, how you are going to search the best model out of the available model. And you can do with the weight sharing and one-shot models. You're going to share the weights among the different parameters that are available with that, right? So in general, in neural networks, we used to sharing the weights between the different parameters instead of sharing the weights at the end based on the different tasks. If you are going to share the weights in the early stages of the network, so that will give you means that is smoother to come up with the result. Okay, the similar fashion. Convolutional neural fabrics, to the paper published there, embedded an exponentially large number of architectures, each path through the fabric in an architecture. There you are going to see in the third one, you are going to share the weight sharing is happening. Okay. So that simplifying one-shot such algorithm. Use path dropout to make sure the individual models perform well by themselves. And NAS is use RL to sample path. And SMASH train hypernetwork that generate the weights of the model. This is DOTS differential able neural network search. I think okay, some of the applications. Okay, so we're coming to the thing as AutoML and jobless through the automations. Okay, how whether the AutoML is coming, it is more like it's been implemented in everywhere. So what is the job loss? Okay, concern about too much automations and job loss, where AutoML will allow humans to become more productive or not. It will eventually reduce the work left for data scientists. Okay, so most of the work is done by the AutoML itself. So more number of data means experts are not required, but it will also help many domain scientists use machine learning that would otherwise not have used it. For example, most of the applications is not been evolved, means not been making use of the machine learning things can be used, okay, without expert. This creates more demand for interesting and creative work. More creative work has to come, and it can reach more number of people, like more certain. There are several number of problems are not been solved. Okay, so many other problems, many unsolved problems, okay, in real time, okay, can be solved using this. So that in that way, the jobs may increase compared to the job loss happening in the other side. But in the other way, means one way job loss is happening, but the other way the other jobs may create. Okay, so those who have unsolved problems been there. Okay. Third, or I'm saying that let's use AutoML to create and improve jobs. If you can think of business opportunity that made feasible by AutoML, robust, off-the-shelf, effective. Now is good time to act on. You can solve different problems using this. Okay. AutoML further benefits and concerns is democratizations of the data science. Directly have a strong baseline, 45. Okay, there are some of the things can be done with that. Okay, when to use AutoML, like classification purpose, regression, forecasting, computer vision, different NLP purpose. You can make use of the things. Okay, in classifications, you wanted to choose which algorithm you wanted to use for the classification. Regression, like similar way, you wanted to forecast, you wanted to do some certain computer vision. Like in computer vision, you wanted to do some like auto annotations, or you wanted to triggering something that you want, something can be done. It automatically can be done such things, right? Based on the context. These are some of the applications can be used. Just that's all from my end. Is there any doubts? Please ask any doubts you wanted to ask. I'm thankful to Dr. Shweta. You've given me an opportunity, but I was not an expert. I tried my best to give the whatever the topic is being given to me. I hope.
Okay, sir. Thank you for. Okay, sir. Thank you for your wonderful session.
Yeah.
Dear audience, any doubts is there? Anything is there to discuss?
Yes, sir. Sir, I have one doubt. Sir, what are the distinguishing factors between deep learning and the AutoML?
See, deep learning also you have to give your hyperparameters and all you have to choose. It will just in deep learning it will extract the features on its own, like but hyperparameters you are going to pass. But in case of the machine learning, traditional machine learning, you have to select the features. There are several feature selection or feature extraction algorithms who are there. You are going to making use of those feature selection algorithms. Okay, for example, if you take the feed forward feature selection and backward selection algorithms were there, right? In case of machine learning, means some of the this is the one taking as another example. But such things are not there in case of deep learning. Deep learning will automatically select a certain features. But AutoML does the feature selection, means it is making use of these algorithms, whatever the algorithms I told. Those algorithms it is making use, but it will not a burden for the use, means whoever is developing. Developer is not bothered about that which feature I want to select and all. It does the things. Okay, if you go to the this one, the very beginning, some one page I showed. It is from the Google slide or somewhere.
Okay.
So where I get this one. So it does the feature selection, set of features. Okay, if you say this n number of automated machine learning algorithms is going to train, right? So all the different scenario, it is using the different features, combinations of some certain algorithms, certain features, certain hyperparameters. It is going to come up with some results.
Okay. Thank you, sir. The sessions were quite informative and quite useful to us.
Yeah, Thank you. I was not that good in presenting the thing. I should thank to Shweta for giving me an opportunity, saying that I should explore this particular topic.
Yes. Thank you, sir. Thank you.
Yeah, thank you.
Yes, audience, is there any others doubts are there still? No?
Yeah, if there are no, I should thankful to the Ramaya University, Ramaya University of Applied Sciences and all the coordinators.
Yeah,
Thank you,
yeah.
sir. Thank you for your wonderful session. Dr.
Yes.
Sunil, sir.
Yeah,
Okay,
dear
audience,
just wanted to request for the slides. It's a very nice talk and a lot of information was there. Yeah, it would be great if you
Most of
can
the
share
things,
the slides.
yeah, slides like most of the things are taken from the automl.org is the one. You can just go through this. Just to
Yeah,
share my
okay.
entire screen.
Okay, definitely. Thank you very much. It's very useful.
yes.
So
Still
Thank you, sir.
any?
Sunil, sir.
This is the website
Sunil,
you
sir,
just
can
go
you hear
through.
me?
This will give automl. This is the website you just go through. There,
Yes,
I have
sir.
taken most of the things from this actually for AutoML. It requires some mathematical knowledge to understand, but it's quite good in this. Here we have many things, their slides, everything. I have taken most of the parts from their slide only for AutoML. This is the slide you can. I hope
Yeah,
it's
yeah.
visible, right?
Thank you. Yeah,
Yeah.
definitely. Very nice.
So please share the slides after this.
Yeah.
To the mail
Anyhow,
you
this is
received,
the
right?
one.
In that mail itself you
I
can
will
share.
share that as well.
Yeah.
I will share right now with you. That is better, I think.
Yeah. You share it to my mail and we sent no today morning. That mail itself you can.
Your mail ID. Okay, I will just send it to the mail.
Today morning we sent the link, no, sir.
Your MSR mail ID, right?
Yeah. Prabha Devi, Shweta will be there.
Okay.
Okay, ma'am. I'll be collecting from sir. I'll be providing you the